technologies, the supercritical water-cooled reactors, the very high-temperature reactor, multi-sort reactor, and why not also accelerator-driven system. Normally, they are still under development. They have a low technology readiness level and even lower licensing readiness level. And they need still qualification. In between, we have the so-called small modular reactors, which may be of different type, depending on their technology. They may be of evolutionary type or innovative type. More precisely, this is the official, let's say, IEA definition of evolutionary design and innovative design. As I say, the evolutionary design are already a number of first-of-a-kind of these evolutionary reactors are currently in operation, and basically all the 51 reactors under construction are of this type. They are said evolutionary because they have, I mean, let's say, limited improvements over existing design with respect to the so-called Gen 2 reactors. And they have, I mean, there is a strong emphasis on maintaining proven design features to minimize the technology risk. Instead, innovative design, as I said, they incorporate major changes in the design approach, also in the fuel, in the materials, in the system configuration in comparison with the existing practice. As I said, most of them, they are still under R&D. And for some of their concepts, we also there is also the need to proceed first with the demonstration plant, and then with the prototype, and finally with the first of a kind. Say that just for your information, the IAEA maintains this ARIS database, which is an advanced reactor information system which collects information on all the type of advanced reactors with information which is very reliable because it is provided by the vendors of the design organization. So here you will find the detailed information both on evolutionary, innovative design when provided by the vendor, and also on most of the small modular reactors. I mean, we also produce on a regular basis this booklet, which are more for policymakers, for governments that they wanted to have just an overview of the reactors, in this case, the evolutionary reactors, the one which are already available on the market. And there are information, very condensed information, basically is an excerpt from our ARIS database. And again, not of course for specialists, but for policymakers, governments that they wanted to have a comprehensive overview of this technology. Similarly, we also produce every 2 years this booklet as a IEA SMR booklet. The last edition was published in 2020. Now we are preparing the new edition, which will be published in September before our general conference. In the last edition, we have collected information on 72 different SMR design. And they are, let's say, categorized on the basis of their coolant or spectrum. So here you will find SMR, which are land-based water-cooled reactor, marine-based, HDGR, fast reactor, molten salt reactor. For the first time, also, we collected information on micro reactors. And not only information, not only on the reactor itself, but also on the associated fuel cycle, and also some consideration on decommissioning and final disposal. So now coming to some characteristic of the different reactor. This is our definition of SMR. They are small modular reactors, so there are two keywords in this title. One is refers to the size. So normally a nuclear power plant which provide electric power in the range of 300 megawatt electric, but this is indicative. We know that there are some design, for instance, that in which each unit is even more than 300 megawatt electrical, and then they are modular. So let's see a little bit more detail what are the key attributes of SMR. So first of all, the story of the modularization. The SMR are intended to be constructed in a workshop, or at least the main components and system of this reactor are supposed to be constructed and tested in a workshop, and then transported as module to the site according to the demand. And this modularization should favor a shortening of the construction time, which we know that in some part of the world has represented an issue, for instance, for the large advanced water-cooled reactor. Since they are smaller, their lower upfront capital cost is lower, so of course they show a better affordability. But another main characteristic is also that they have a flexible operation, so they are also good for remote regions, for small grids, and also very good. I mean, maybe the best nuclear technology to be coupled with other clean energy sources, like, for instance, renewables. So they promise to be particularly suitable to be integrated with renewable in so-called hybrid energy system, or integrated energy system. And they are, for this more or less the same reason, they are also particularly suitable for non-electric application of nuclear power, like hydrogen production, desalination, district heating, and other industrial applications. There are SMR of different categories, basically, as I said, of any reactor technology. So it is more or less what I already said in the previous slide, that there are SMR of any major line of technology. I cannot, of course, I don't have time to comment on that, but this is the map of the global SMR technology development, and you can see that basically there are technology holders and also interested countries, more or less all over the world, in all the different regions of the world. What can we expect in terms of deployment? Here we have summarized the information as provided by the vendors, and this slide shows the expected deployment in this decade. Basically, we expect that there will be the first of a kind, or at least one unit of several different SMR of different technology, from integrated pressurized water reactor to gas-cooled reactor, even, why not, fast reactor. So this decade is a decade devoted to the demonstration of the technology and also the safety case, obviously, and then the large deployment following possibly the economy of mass production is expected beyond 2030 and also beyond 2040. Of course, when we talk about advanced reactors, we cannot forget the case of fast reactors. For several reasons, at the moment there are only a few fast reactors in operation. Only 2 industrial-sized reactors in Russia, then the PFBR under commissioning in India. The other are test reactors like FBTR, Cephren. Here you can see bore 60, but of course in this context, and also in international context, it's very important that the panel somehow refers to the MBIR reactor, which is supposed to replace bore 60 in the red. Here we have also some fast reactor under construction, like the CFR 600 megawatt electric construction in China. Actually, two units of this reactor under construction, and then the recent announcement of the start of construction of the Brest 300, which will be the first industrial size lead-cooled fast reactor, and then also very innovative concept like the natrium SFR which combines a sodium cooled fast reactor with a molten salt energy storage. We know that there is a famous person, Bill Gates, behind this project. Another category is molten salt reactor. There are so many different classes and family of molten salt reactors that we thought that it was good to try at least to summarize all of them and the main characteristics of this different molten salt reactor. And on the right side of this slide, you can see the taxonomy related to molten salt reactors. There is such a multiplicity that is also difficult to follow all the different streams. However, to make this clear, we have just finalized the technical report series on the status of molten salt reactor technology, which you can find the different molten salt reactors and also their main characteristics. Now, just to conclude my short presentation, of course, there are challenges in the successful deployment of small modular reactors and looking ahead, also innovative reactors. But first of all, of course, there is the need to demonstrate their safety, their performance. This is true, of course, more for the most, let's say, innovative, revolutionary design. It should be less demanding when we talk about the SMR, which rely on existing technology like integral pressurized water reactor, or compact pressurized water reactor, also boiling water reactor. The other main point is that, yes, since there are small, of course, small power, they cannot rely on economy of scale, as was the case for all the reactors so far. They have to rely on economies of serial production, but the nuclear industry never experiences that. So, of course, this is in principle a challenge, which is very important from the economic viewpoint, but of course, it has to be proved. The other very important issue is harmonization and standardization, because this is essential, in our view, in order to, say, enable the global deployment, the extended global deployment of a standardized fleet.
Stefano, I'm sorry, we're running a little bit behind the schedule.
I finished. I'm just concluding with this slide. And this standardization should be pursued both at the industrial and also at regulatory level. At regulatory level, of course, which means, let's say, also try to develop a common set of internationally recognized requirements, but of course by maintaining the national responsibilities. And then there is the big, let's say, Pandora box that we have to open related to the related infrastructure for deployment, and this may be a particular issue, in particular in embarking countries. With that, I've finished. I can skip the last two slides and over to you.
Thank you very much. Anybody wants to take this opportunity to ask the questions to Stefano Monti on his presentation from the speakers who are online? Any questions? We have one question from the audience. If you could help with the microphone.
Yeah, thank you. My question, my name is František from Slovakia. We are developing technology for Earth crust penetration very deep. And say our system, the weight is about 700 tons. And we need energy source for our machines. My question is, could you micronize that kind of reactor down to, say, 5 megawatt? I saw some kind of mobility in this action. How it's the weight, approximately 5 megawatts, if we could integrate it in our systems for deep penetration? The estimated weight.
Well, Should I respond?
Yes, Stefano, if you can respond to this question.
Well, of course,
how much is going to wait 5 megawatts?
Okay, the IEA should remain technology neutral. So of course, we don't want to comment on specific reactor technology. However, we have seen that yeah, there is an increasing interest also for this micro reactors. So not all over the world, in some region of the world, for very particular application. First of all, of course, remote regions that they need a very limited power, but not only for electricity, also for other purposes. And due to their flexibility, they are particularly suitable to be integrated, for instance, with the variable renewables like wind and solar. However, it's difficult to respond to specific question because, first of all, because also for their particular application, the available information, the free available information sometimes is pretty limited. Also on our side, we had a technical meeting on micro reactors in April last year. And of course, it was important above all to understand the main purpose and features of these reactors. However, the information, as I said, the technical information are still very limited, and there is basically no operational experience. And as you know, all the attempt to harmonize both of the industrial and the regulatory process, the IEA, is heavily based on operational experience. And we have also very limited understanding of the associated cost, how these reactors can be competitive with equivalent energy sources, in particular in liberalized market. From this point of view, we tried to learn from let's say,
Stefano, thank you very much for this detailed answer. I think it was a hard question actually to respond in such a limited, and we're not here on the micro reactors, but there is a big number of specialists in the room. So if you can liaise with them later on, and it's not an easy question because it depends on the technology and on that will be used and what applications. But we have to move to our next speaker, Dr. Tatiana Ivanova from NEO-OECD. She's the head of Division of Nuclear Science and has more than 30 years of experience in both the development and safety assessment aspects of nuclear energy. So Tatiana, hi, we can see you. So if you're ready, please go ahead with your presentation on the FIDES success story and experience of joint research program implementation. Thank you.
Hello, Alexander. Hello, everyone. I would like to thank you, to organizers, for assembling this panel session, first of all. And it's my great pleasure to join it and present the new multinational framework for radiation experiments that have been launched last year in the Nuclear Energy Agency of the OECD. Next slide, please. Next slide, please. Thank you. Let me start by introducing my organization. The OECD Nuclear Energy Agency, established 33 years ago and located in Paris, is the intergovernmental body that brings together experts from the countries with the deepest experience and capacities in the broad range of civil nuclear energy technologies and policy issues. 34 countries from the Americas, Europe, and the Asia Pacific are members of NEA. They operate about 87% of the world's installed nuclear capacity. Russia has joined the agency in 2013, and since that time, we have had a very productive collaboration with many Russian institutions. Next slide, please. Why FIDES? Why we launched this ambitious framework? As you know, the safe, reliable, and efficient operation of nuclear power plants require nuclear fuels and materials to evolve. and to address the current issues that nuclear energy is facing. Achieving these requirements, we need solid experimental evidence, which can only be obtained from the test facilities with the ability to perform neutron irradiation under representative steady state or transient conditions. However, the number of available test facilities around the world are in significant decline. As you know, in the past 5-6 years, several major research reactors that provided services for over 50 years have been closed. And this includes the Halden reactor in Norway, closed in 2018, the Osiris reactor in France, the GMTR in Japan, the NRU in Canada, among all others. The regulators and their technical support organizations, research organizations, and the industry, they all require fuel and material testing capacities on an ongoing basis. Next slide, please. To help our member countries in mitigating the experimental gap created by the closure of research reactors, the ENA has engaged with industry, regulators, TSOs, and research institutions and organized several international workshops over the course of 2018-2020 and held like a myriad of bilateral discussions with their main stakeholders. As a result of this extensive discussion, the international community has decided to establish a new NEA joint undertaking framework for irradiation experiments, or FIDES, and its joint experimental programs, or JIPs. FIDES has been created in a strong coordination with the NEA steering committee and standing technical committees. And thanks to valuable and thoughtful and proactive input from all the FIDES members and the cooperation across the agency, the first FIDES agreement has been finalized in March last year. Next slide. Please. FIDES has been built as a under Article 5 of the NEA statute to bring together a network of key research reactors around the world to perform high priority experiments with fuels and materials on a cost sharing basis, and in order to safeguard the experimental knowledge for future generations. For the moment, we've received proposals for 9 joint experimental programs. They cover a wide range of experimental needs identified by the FIDES community and will be conducted at several existing research reactors and the research reactors under construction. And you can see the red box on this chart that shows that we're counting on the research reactors that will be constructed in the future, and this includes MBIR reactor. Sorry. Next slide, please. The program of work for the first mandate, or the first program of first agreement, includes 4 joint experimental programs and the project on data preservation and quality assurance. The first program is a program for quantified thermomechanical clad load mechanism during light water reactor flow transit, or power to melt and maneuverability, or P2M, how we call it. And this program will be performed at the BR2 reactor in Belgium and the post-irradiation examination facilities called LECA and STAR in CEA, France. The next program is called INCA, or in-pile creep studies of ATF cladding. It will be performed at the LVR-15 material test reactor in Czech Republic and post-irradiation examination facility in Czech Republic. Next slide, please. And another program will study fuel road behavior under loss of coolant accident conditions, or LOCOMIR, and will be performed at the MIR M1 reactor in Russia and RER. And finally, the high burn-up experiment and reactivity-initiated accident HERA will be performed in the transient reactor test facility or treat reactor in INL in the United States, and the nuclear safety research reactor NSRR in GE, Japan. Additionally, design of all these experiments will be supported by the calculation analysis where all interested parties will be involved. Next slide, please. Next slide, please. Thank you. As you can see, all the experimental programs that I have listed and I have presented, they will deal with the conventional fuel, light water reactor fuel. This slide shows you the status of the new endeavor launched by the NEA. It was launched in March 2021. It includes 27 organizations from Belgium, Czech Republic, Finland, France, Germany, Hungary, Japan, the Netherlands, Russia, Spain, Switzerland, and the United States, and also the European Commission. The budget of this project is 23 million euros. That includes the contributions from the members of the FIDES and the contributions from the core groups. The FIDES is governed by the governing board and the technical advisory group. And the experimental work will be performed, as I said, at 5 research reactors around the world, and the experimental work has started. Further steps include several initiatives under the umbrella of FIDES. One of them is the project on data preservation and quality assurance, and another is education project that will jointly be conducted by the FIDES and the NEA Nuclear Education Science and Technology Framework, or we call it NEST framework. Next slide, please. As I have already mentioned, this experiment will help the safety assessment and design of the new fuels, including ATF fuels. But we have new reactors, we have innovative reactors that Stephanie Monti has already mentioned, like SMRs. We have advanced reactor with fast spectrum, and this will require additional experiments that should be performed in new facilities. And we are engaging with the new facilities, Jules Horowitz reactor that is being built in CEA in France, and the multipurpose sodium-cooled fast neutron research reactor in Bir that is being built in Russia. And we will organize the joint workshop with FIDES members where we will discuss the future programs that can be conducted on these reactors once they have been built. And of course, these experiments will include the testing of advanced fuels, including advanced fuels for fast reactors. And of course, the MB reactor provides a unique opportunity, once constructed, a unique opportunity to test this advanced fuel. With this, I would like to finish the presentation. Thank you for your attention. I'll be happy to take your questions.
Thank you very much, Tatiana. Thank you for this high praise of MBR reactor. And we're going to be in the next couple of presentations speaking more about the MBR. We have time for one question. If there is a question in the audience who want to ask to Tatiana. Well, no question from the audience, Tatiana, but I have a question of my own. We can see that finally the FIDES getting some traction, and we want to congratulate you with this. So if you can give us some hints on how difficult it was to put all these different countries together in the joint program, and whether you feel the increased interest and increased desire to do the joint research in the nuclear in the recent years.
Thank you, Alexander, for the question. It's been not an easy task, I can say, but the closure of Halden reactor, in a way, revitalized the community. And it is clear that without the sustained experimental infrastructure, it will not be possible. Any progress in fuels and materials will not be possible. It was a motivation for our countries, for the member countries, to join the framework. And in the beginning, after the closure of Halden, it took time just to get to bring this community together to discuss industry and safety and R&D, the needs. What are the needs? What are the critical and high priority needs? I can say it's been not easy task, but with the help of our members and their proactive engagement, we managed to launch it within 3 years, which I believe is a reasonable time frame. And it shows that the international collaboration is very much appreciated and understood as the instrument for further development in the nuclear industry. Could you repeat your second question?
Well, that was, I think, the main point and question there. Thank you very much for this detailed introduction of the FIDES program, and it's great that you're supporting the fast reactor research. Hopefully, we're going to be, it will be possible for us to do some joint programs together under the umbrella of NEO-OECD. And now we are moving to the next speaker, but before we go to the next presentation, I wanted to give you a small slide just to explain what difficulties we are facing right now in terms of research reactors in the world. So you all know that the number of research reactors is declining, and we expect that by the end of 2030, there'll be much less of research facilities in the world. But what is probably more significant and important is you can see that the line on this top graph stopped growing back in the 80s and 90s. So after that, there haven't been lots of construction of research reactors, and most importantly, the big research reactors such as 100, 150 megawatts haven't been constructed in a long time, if not to say ever. But the problem currently for the industry is the construction competences and the ability of the constructors to build these highly complex facilities in the time limits that we have for these projects. And we in Rosatom have this knowledge and the people who are able to construct such complex facilities. So we're going to be moving to the presentation of Mr. Gennady Sakharov, who is Director of Capital Investment, Construction Supervision and State Expertise of State Atomic Energy Corporation Rosatom, and he will tell you about digitalization and innovative technologies, construction of a unique MBR research facility. So I give the floor to Mr. Sakharov.
Коллеги, добрый день. Меня зовут Геннадий Сахаров. Я являюсь директором.
Dear colleagues, good morning. My name is Gennady Sakharov, and I am heading 2 projects, MBIR and Brest 300, that were mentioned today. I'm also the Director of Capital Investments, State Construction Supervision at Rosatom Corporation. As per the federal program, Rosatom today is building the facility for MBIR fast neutron reactor. It will be one of the most powerful reactors today in the world, and on its basis, Rosatom is building an international research center. And Rosatom is inviting international partners to take part in this project. As my colleagues have said, it's an innovation reactor, and it's being built with innovation practices which are the best in the world. On this slide, you can see the innovations that we have used during the construction. First of all, the project management of the construction site, then the development of design documents, modeling of the construction site. The third point is very important. For the first time in Russia and for the first time in Rosatom, we have used a new business model based on FAC1 contract, which is about the use of consortiums. And to assess the cost of the project, we developed the resource model, and we keep monitoring the implementation of the project with the remote monitoring system. We are using information modeling technologies for ambient construction in order to minimize the changes in the project due to some errors, minimize additional works, and increase the efficiency of the management of this project. We can create transparency for investors that we are looking for at the moment, and this technology allows us to show transparency for our investments. Then the construction information model. We use it to get real information about the time of the project, the construction works, and many other processes. And we can also coordinate all of the stakeholders at the construction site, various contractors, suppliers, and we also cut off on the time by managing it really efficiently. This project is a mega project, and cost and time is very critical here. Implementation of the construction project by the consortium. It's a new business model for us. It's closer to collaboration, to digitization, and this project allowed us to test this consortium model. We have a consortium agreement with the leader. Inside we have contractors, designers, suppliers of materials, insurance companies. So all of the risks of the projects, they are distributed among the parties. And we started the consortium at the very early stage. 20 to 25% of technological solutions, we had to change them. This model will also be used for our other projects, including NPP abroad. Next, remote monitoring. First, we use drones, terrain scanning, 3D modeling. We can provide visualization of construction works, which also adds to the transparency. At this stage, it's an example of what you can see using site remote monitoring. You can see that using the tools, we can find out that with this power of facility, the area surface is 469 square meters. So we found from deviations from our original design. And Rosatom is developing similar methods right now. And we will be using them at our other facilities. Next, as I said, an important tool for construction is exchange of technologies, which allows us to compare the physical quantities and the time it takes to implement the project. The current status of the construction project. In 2020, the unit has passed the state assessment. We plan to finish the project by 2028, but since we have used a new business model and new technologies, we now think that we can commission the project by the end of 2026, and this will be quite an achievement. Currently, the construction is in progress at all of the parts of the facility. As I said, we use the project-based method. Since we use a lot of staff in this project, they all can collaborate efficiently, and its close cooperation ensures security and reliability of MBIR. And finally, a couple of words on the infrastructure of the International Research Center. We have internal boundary and external boundary, so that we can invite visitors from outside at the facility and have all of the infrastructure that they would need. We are building a modern center with sports facilities, social dining facilities, so it will be a very modern and international center. This is all I have to say. Thank you so much. It's quite a unique project about the part about acceleration of your project, because your planned time will be 2 years less. So what exactly are you using to avoid risks and to accelerate the process? I would say that one of the key factors that allowed us to cut off 2 years is the use of this new business model, which is consortium, because all of the parties at consortium are highly motivated. They got committed from the start, so the risks are distributed and the profit will be distributed. We have a consortium committee that meets once a month, and they always come up with various technological solutions. So yes, I would say that it's a key component to our success. Thank you very much. I just want to clarify that we are speaking about construction consortium. And we'll now show you a video.
Safe, sustainable, effective. Development of the new nuclear energy technologies requires new experimental tools. Rosatom is implementing the MBIR project. This multi-purpose sodium-cooled fast neutron research reactor has the design and technical parameters that will enhance and accelerate referent research and development of innovative technologies. MBIR's modern infrastructure will allow to conduct testing of construction and absorbing materials necessary for development of Generation 4 reactor technologies, study promising types of nuclear fuel, fuel rods, and develop technologies for closing the nuclear fuel cycle, produce isotopes and radiopharmaceutical raw materials for different applications, and carry out the production of modified materials. Conduct research with neutron beams application in the field of medicine, fundamental and applied physics. The reactor core will be equipped with 14 non-instrumented channels for placement of materials test rigs and irradiation devices, 3 instrumented experimental channels, and 3 experimental independent loop channels with various autonomous coolants separated from the main sodium circuit. Core blanket can also be used to place experimental and isotope assemblies. There are 6 horizontal and 8 vertical experimental channels outside the reactor vessel, which allow to conduct research in neutron flux of various spectra. With its unique technical characteristics, the MBIR reactor will unlock new opportunities for development of nuclear energy and will become the backbone of future innovative reactor technologies.
Yes, so this is a video presentation of the MBR reactor, and now we're going to have a few words on the MBR and the International Research Center, and then I'm going to be taking off my moderator hat and putting on my presenter hat. We're going to go through a few interesting points here. So first of all, the 2-component nuclear energy. So this is a decision which has been made by Rosatom, and we're already moving towards this direction. For this vision to be realized, we need to have the fast nuclear power plants, the fast neutron nuclear power plants, and they will be working in parallel with the PWRs or VVR in our case. And this will allow us to gradually close the nuclear fuel cycle and basically solve a number of problems related to the, first of all, availability of the fuel, and secondly, treatment of the radioactive waste. So in terms of the current experimental infrastructure, we are proud to say that Russia right now probably the only country in the world which has all the infrastructure needed to develop the reactors from the beginning, from the design stage to the implementation. As, for example, such unique facilities as BFS, as we call it. So this facility allows you to design the cores of the reactors, and you can see that all major projects which are currently under construction or have been realized, they've all been researched at this facility. Now we have the only research reactor, fast research reactor with a sodium coolant bore 60, which is currently available to the international community for research and development. And when MBR will be put into operation, we're going to move the experiments from bore 60 to MBR, which will allow us to continue the cycle of research without any interruptions. And we already made the justification of such transition possible. Regarding the MBR reactor, this is a 150 megawatt fast research facility with sodium coolant, as you've seen from the video. Previously, we were hoping to commission it in 2028. Right now, thanks to our construction leaders, we are looking at an even shorter period, and we are looking to start research earlier in 2027. In terms of other fast research reactors which are currently under design or operated, you can see that there's not that many countries which possess such a technology. Basically, we can say that China, India, United States is trying to restart their FAST research program, and VTR is only in the pre-project study phase, and Russia having the BOR 60 and MBR, which is coming to replace it. So we believe that the future of the nuclear research will be centered in Russia, and we are open to invite international community to work and to use the research infrastructure that we have, because we want to develop the market of the fast reactors. So in terms of experimental capabilities of the MBR reactor, it's called the multi-purpose fast research reactor because it's not only the irradiation research which will be possible for fuel and structural materials, but also there's a number of other production activities and research activities which will be possible in this facility. So for example, we can produce different types of isotopes on this facility. Due to availability of horizontal and vertical channels, we can do the basic and applied research with ultra-cold neutrons, and we're going to have a presentation during this session later on this topic as well. It will be possible to test new equipment, engineering, design and configurations, and also it will be possible to do the verification of computer codes and different types of safety studies which are desperately needed for the launch of any new facilities around the globe. So in terms of MBR design features, the main features, as you've seen before, is the places where we can conduct the research, but probably what is one of the key features of the MBR is independent loop channels, which will allow us to use different coolants, not only sodium, but also other types of coolants. And here you can see the parameters of such loop channels. In addition to sodium, we are planning to introduce the lead bismuth, and gas loops. This is the decision that's been made by our scientific council already. And the facility allows us to have 5 loop channels in total, technically, and out of which 3 will be working simultaneously. So what are the problems that we are going to solve with autonomous loop facilities? So most importantly, we can test the limits of safe operation of fuel rods and behavior and damage under conditions of variable loads and exceeding the limits of safe operation. Basically, there is insufficient or not studied phenomena in reactor conditions for different types of fuels and for their behavior. There are also a number of questions on the fuel behavior in different types of coolants. And that's something that you need a research facility to test in. You cannot put the new compositions in the big commercial reactors. You need to have a very specific types of reactors with the controlled parameters and characteristics. Russia have put together the international research program, or multilateral program as we call it. As you know, we are the leaders in the fast reactors, and therefore we put together our understanding of what has to be researched and where we have to be moving in terms of the next steps, and where we'll be looking for new development. And we put this in this research program, and it is available on the website of the consortium leader. This is the company which will be managing our consortium. And also, we have provided this program to the NEOECD, and it is available on the NEOECD website as well. So there are different areas in this program that we are focusing on. Of course, this is the research into advanced fuel materials performance, research into new and modified liquid metal coolants, research in different structural materials, etc., etc. And we are currently working with our international partners to identify the areas which could be interested for them to conduct a joint research under the umbrella of one of the international organizations. I'm not gonna spend too much time on this slide, but basically here you can see the horizontal and vertical test channels, their composition, and what will be possible to do on these channels. Here I want to draw your attention to silicon doping, and there is quite an amount of silicon doping which can be done at the MBR facility. So we're talking about 60 tons of silicon per year, doped silicon. And also there will be possibilities for different medical applications and other type of activities. So in terms of construction of multipurpose fast neutron research reactor, we want to stress here that we believe that this infrastructure supports the sustainable development goals of the EIE. There is a, we'll come back to this later, but the key mission of MBR reactor is basically the provision of full cycle high-tech knowledge-intense services, pre, under, and post-irradiation, and creation of international scientific platform to address current challenges in the field of innovative nuclear technologies. So we are creating the global center of competences for fast reactors. We're bringing in the international community together, and we are creating the platform where the knowledge could be shared through the multilateral programs and through the joint research activities. For this, we created the consortium, International Research Center MBR Consortium, which is composed of two types of members. This is the principal members, associated members. The principal members are those who join in the consortium during the construction stage of the reactor. They have a preferential terms of participation. They also get a guaranteed share of the MBR reactor resource. They have the right to acquire the services at basically at cost, you can call it that. And they get the permanent seats at the management bodies of the consortium, and their voice is there heard well and loud. The associated members, this is those who are interested in the MBR reactor and its parameters and facility, but they're not ready to join during the construction. They want to have the facility available for them for the research right after, and right after that, they are ready to join. So we call them associated members. They already can participate in the scientific body of MBR and get involved in formulation of different research activities, but they'll be joining later, so the price for them is higher, and also there are some limitations on what kind of place in the MBR they can get and what kind of reactor resource they can count on. Okay. Can you change for the next slide? For some reason it's not moving. Next slide. If for some reason the clicker is not working there. Okay, but whilst we're fixing the presentation, the next slide, we basically focused on the composition of the consortium. What kind of governing bodies do we have? So we have the IRC MBR Council. This is the top governing body where we're going to have the representative of all the principal members. This is the top decision-making body. And we have management committee, which will be focusing more on the day-to-day operations and the control of audit of the construction, and audit later on of R&D budgets. And we have the advisory board. This is probably one of the key bodies that we are focusing right now in this project. And there have been a huge step, thank you so much for the slide. Yes, go to 16. So there have been a huge step in terms of creating this advisory board this year. So we already have a number of participants who delegated the members to advisory board. And this is basically will be the brain of the consortium. That's where we're going to be formulating the different research activities, the joint research activities. That's where we're going to be basically analyzing how to put all these different research activities together, because it's not a simple task to accommodate all the different research in one reactor. So the advisory board meets once a year at least. We have already representatives from Russia, France, Korea, and Afghani, and we are working with other partners to finalize the creation of the advisory board in the first quarter of this year. The chairman of the advisory board is Professor Kalmykov, Dean of the Faculty of Chemistry of the Moscow State University and Doctor of Chemical Sciences. And we're going to have 6 scientific committees in this advisory board on materials, safety, code verification, theoretical physics, non-energetic application, and closing of nuclear fuel cycle. So here's the snapshot of our partners around the globe with whom we are talking of joining the consortium. We are quite an advanced stage with certain partners. We are under discussion with others, but we hope, as there is a growth and increased interest in the future of nuclear industry, we hope that this partnership will develop and there will be more participants of the consortium at the later stage of the construction. So this is it in terms of my presentation. We're going to run the quick video in terms of consortium right now to give you the final understanding of how the consortium will be working.
Uniting the efforts of the global community around joint priorities, Rosatom constructs a unique research infrastructure which is essential to the transition to 2-component nuclear system. The multi-purpose research reactor IMBIR will provide a substantial extension of the possibilities of experimental research and allow to decrease the time needed to introduce new technologies in the field of nuclear energy, industrial, medical, and scientific areas. An international research center will be established on the basis of IMBIR. Scientists and experts from all around the world will take part in its operation. The IRC will be functioning in accordance with the consortium agreement, as well as in conformity with international law. The consortium will manage the scientific research program, regulate the distribution of rights to receive services among the members, provide financing at the construction stage, and during the operation of IMBIR. The consortium offers 2 forms of membership, such as principal or associated member. The principal members, who finance the construction of IMBIR, will have the option to receive the irradiation services in the reactor's core for a special price, as well as the right to participate in the governing of the consortium and the development of the scientific program for the entire lifetime of the reactor. The associated members who join the consortium at the stage of the operation of the reactor will have the possibility to acquire the irradiation services in the unoccupied cells in the lateral blanket at the market price, and the right to participate in the scientific research program as defined in the consortium agreement. The main global advantages of the consortium are: members can cut the expenses in comparison with the construction of their own research unit, the possibility to participate in the multilateral research programs conducted in the reactor, as well as the right of managing the acquired part of the resource with the possibility of distributing it to third parties on the terms of the consortium agreement. Upon entering the consortium at the construction stage, principal members will receive significant technical, scientific, and competitive advantages. To join the project, it is necessary to choose a type of membership, agree on the amount of the resource to be acquired, conclude the consortium agreement, and appoint the representatives for the governing bodies of the consortium of the International Research Center on the basis of the IMBIR reactor.
So we have a time for one question, if anybody has a question to me regarding the International Research Center. If not, we're going to move to the presentation of our distinguished partners from around the globe. And the first up is Mr. Ho Xinghai. He will talk about the development of fast reactor and related fuel cycle in China. And it's, I guess it's one of many interesting presentations, especially taking into account that China is one of the major players in the development and implementation of fast reactors alongside Russia around the globe. So, Mr. Ho, the floor is yours.
Okay, so you can hear my voice?
Yes.
Okay. Okay, now start. I feel quite pleased to join this panel and give a presentation to show the development of the fast reactor and related fuel cycle in China. Firstly, I'll give a brief introduction of the current status of nuclear power in China mainland. Now, China has established the whole chain of nuclear industry by the end of last year. Totally 53 nuclear power units are under operation, with another 20 units under construction. So at present, China ranks the second in the whole world by total capacity of operation and construction.
Mr. Ho, just a quick question, sorry for interruption. Do you have a presentation on currently, or because we cannot see the presentation?
You cannot see me?
No. We could see it in the beginning, but maybe you can start it again.
Okay.
Oh yes, now it's on. Yeah, thank you.
Okay. 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 Sorry. So you can see from the map that most of the nuclear power plants are located in the east coast of China, which is also the most developed areas. In recent years, China industries and institutes developed some new technologies focused on generation 3 nuclear power plants and also some SMRs. Among them, the HBR1000 has been connected to the grid, and HDRPM, which is the first gas-cooled reactor, generated electricity just several weeks ago. In recent years, the carbon reduction brings new opportunity to nuclear power in China. Maybe you have heard that China has promised to reach carbon peak by 2030 and carbon neutrality by 2060. This is a very heavy burden to the whole industry. So we believe that nuclear power will play a key role to reach such a high target. So in the government reports by the Premier last year, it is promised that China will actively promote the development of nuclear power. This is a great driving force for the industry. So this picture shows the prospect of the 2050. Now, this is a rough estimation by some organizations. This is not official, but it is quite a precise estimation judged by our institute. From this estimation, that nuclear will take 15%, which is triple of the current share. So this is will be a very fast development. To reach such a big scale of nuclear power, breeding is necessary for China. So to reach a better utilization of natural resources, fast reactor is necessary for Chinese industry, which will help to transfer the fertile nuclides to fissile. We have proposed a three-step strategy. Also, this is not official or not accepted by the government, but this is only a proposal. And now we can see that we are just on time to follow this strategy, as we will reach the first criticality by the demonstration fast reactor next year. So we are just on time to follow this strategy. The next step is a commercial fast reactor in around 2030, which will demonstrate the economic features of a sodium-cooled fast reactor. And the concept design is ongoing. So the first step is the experimental fast reactor, which was constructed in late 1990s. It was located in the southwest suburb of Beijing, around 45 kilometers from the city center. It has the thermal power of 65 megawatt. Because the time is limited, I don't think it is necessary to go to the details, and I would only want to mention that for the first several loadings, the core is loaded with the uranium dioxide. In the long term, this reactor is scheduled to be loaded with the MOX, so it will be very good irradiation facilities for the self-development of our own nuclear fuel. And the second step is China demonstration fast reactor, which was and construction. To be exact, it is already in the phase of commissioning because the major construction has completed last year, and now it is under the installation of key equipment. The current prediction is that the first criticality will be in the early of 2023. This reactor has the thermal power of 1,500. The third step is the commercial fast reactor, which will reach a thermal power of around 3,000. And for the fuel, the current design takes MOX, but in the longer term, the metal fuel is also considered. The commercial fast reactor will demonstrate some innovative designs, including the supercritical carbon dioxide energy conversion system. About the nuclear fuel cycle, I think it is necessary for any nation which have a big scenario for the development of nuclear energy. So the main goal is to utilize uranium to the largest extent. So we will recycle all the uranium, plutonium, and the major actinides. Currently, we have built several facilities to demonstrate the closed nuclear fuel cycle, including the experimental fast reactor I just mentioned, and also a MOX lab and a reprocessing and radiochemistry lab, and also a experimental size reprocessing pilot plant under construction. In the longer term, by 2035, China will try to establish a commercial demonstration plant to process around 800 tons of spent fuel per year. And also this project will demonstrate the closed fuel cycle of the whole nation, of the whole industry. In the longer term, by around 2050, I think a metallic fuel will be introduced, and at that time, the whole MA recycling will be demonstrated, which will try to solve the question of highly radioactive nuclear waste. So the longer term scenario is that by 2050, PWR will reach around 200 gigawatt, and at the same time, a fast reactor will be facilitated. Two steps. As the first step, the fast breeding reactors will be the main force, and in the second step, the MA transmutation will be built, and finally realizing the whole actinized utilization. So in the future, there will be a binary structure in China, which consists of innovative PWRs and also fast reactors with MA transmutation. Finally, I would see that in the whole history of fast reactor development of China, Russia played an important role. And this photo shows the signing ceremony for the CEFR project between Russia and China. And both presidents of nations were present. And this photo shows the then Deputy Prime Minister of Russia visited the CEFR in 2011, and nowadays the cooperation between the two nations are still undergoing in many areas. So the concluding remarks: so China will expand the nuclear power to a much larger scale in the coming decades due to a fast-growing economic development. A fast reactor and nuclear fuel cycle are necessary if nuclear power is going to play a key role to meet the future power demand. Russia helped a lot in the development of fast reactor for China in the past decades, and we also look forward to further and deeper cooperation in the future. So that's my presentation. Thank you, and I welcome any question. Thank you.
Thank you very much, Mr. Ho. Any questions from the audience or from the fellow speakers to Mr. Ho? I have one question to you, or maybe two. We'll see how it goes.
Yes.
You showed us quite an expected development of the fast reactors in China, and we understand and know that you have a quite extensive research program in relation to this expansion. The question is, at which facilities are you planning to conduct such a research, and whether you think it is enough, or whether you see that the infrastructure that you need is all the necessary infrastructure is in place, let's put it this way.
Okay. So currently, for fast spectrum irradiation, now we rely on CEFR at present. But as you know that the CEFR is, due to its design, it is quite weak at irradiation of nuclear fuel and structural materials. So our next step or a near-term plan is that China will build our own high flux irradiation reactor. But at the same time, we are also trying to find international cooperation, including based on the MBIR. Thank you.
Thank you very much for this comment. And also, one of the last questions, sorry, we may be a little bit running late, but from your presentation, is it correct to assume that you're going to be focusing on the breeder fast reactors more than on the burners in terms of the future mix of reactors?
Yes. I've mentioned in one of my slides that as the first step, we will focus on breeding. But in the longer term, as we will have a binary structure, we will have a large scale of PWR profile. So definitely we will try to find a way to transmute all the MAs produced by PWRs and also fast breeder reactors. So I believe that transmutation reactors will be also introduced in several decades. And now basic research are undergoing.
Thank you very much for these answers and for very nice in-depth presentation. So we are moving to our next speaker with a presentation overview of Korean sodium-cooled fast reactor program based on Generation 4 technologies. And the speaker will be Mr. Yo from J-Hook, Division Director and Versatile Reactor Technology Development of KAIRI. Do we have our speaker?
Thank you.
Yeah.
Can you hear my voice?
Yes, we can see you
okay.
well and see your presentation. Go ahead.
Okay,
the floor is yours.
Perfect. Yes. Thank you, Mr. Dragunov. Hello, everybody. It's my great pleasure to be invited in this event and introduce the development program in Korea. I'm Jae-hyuk Oh from Korea Atomic Energy Research Institute, KAIRI. And currently, I'm managing the SFR development program. Okay, let me share my screen. Okay, so now let me talk about the status of Korean sodium-cooled fast reactor program. It's gonna be a bit short. Okay, I usually begin with this slide when introducing the Korean SFR program to share the special circumstances of nuclearization in Korea. As you may know, currently 24 nuclear power plants are in operation in Korea, and most of them are light water reactors such as PWRs. However, the spent nuclear fuel from those PWRs has been stored in the interim storages at individual reactor sites, but the interim storages are approaching their capacity limit as well. So we are trying to set the national policy of spent nuclear fuel management, but it has not been determined yet. So we are still weighing two options of direct disposal versus final disposal after reducing its volume and toxicity by using sodium-cooled fast reactor coupled with pyroprocessing technology. Actually, in Korea, we cannot help picking the latter. I mean, the final disposal option coupled with pyroprocessing and separate technology. This is due to our situation such as small territory, high population density, and even some political issues as well. So we need a fast reactor option coupled with pyroprocessing to reduce the amount of spent nuclear fuel and its toxicity. That's why we are developing a sodium-cooled fast reactor as a TRU burner to solve the spent nuclear fuel management issue. So we have developed our own SFR design concept since the middle of the 1990s, and we got the Kalium 600 design in the middle of 2000. Actually, Kalium 600 was a paper blank, but based on its design, we have developed the 150 megawatt electric TRU transmutation demonstrator as a spent nuclear fuel management option. It's called the PGSFR. PGSFR stands for Prototype Generation 4 Sodium-Cooled Fast Reactor, but its original construction plan has been suspended complying with the National Nuclear Phase-Out policy in Korea. So now we are trying to take the two tracks of SFR development. Track one is to keep developing PGSFR as a TRU transmutation demonstrator. We are preparing the future plan targeting the domestic construction of TRU transmutation demonstrator, reflecting the decision of the government review committees on this issue. The other track is to develop an SFR-based power generation reactor as a spin-off technology from the PGSFR concept. This new SMR development project has been just started last year with a new grant of Korean government. This slide shows actually the overview of the PGSFR development program as PRU transmission demonstrator. PGSFR project was getting started from 2012, and based on the government support, SFR agency was organized at CARI to manage the whole project, including funding, engineering, licensing, international cooperation, something like that. CARI has led whole project, of course, and domestic partners such as EXPO ENC and Doosan Heavy Industry have been involved in the design development phase. Most of all, Argonne National Laboratory in the United States also participated in the project as a key joint design partner, which made PGSFR design level high enough to be ready for its next phase. So far, PGSFR design has been completed to make a kind of equivalent step analysis report so that we can respond to dedicated step review processes in the future. The second track of SFR that we are developing is an SFR-based power generation reactor toward the SMR market. Its name is Salus. The electric power output of Salus is 100 megawatt with flexible range. And we are using spin-off technologies from the PGSFR design. Actually, Salus 100 is pursuing not a PRU burner, but a power generation reactor with a low fuel cycle. Our target is actually the global SMR market. So to be ready for facilitating global export of Salus 100, we are now looking at the opportunities of the Canadian SMR invitation as a non-LWR-based reactor system. Currently, CARI is taking into account the pre-licensing vendor design review focused on the Canadian regulatory system. More specifically, CARI is planning to apply for the VDR phase 1 to identify a licensing viability of our power generation SFR design earlier. So we think this approach could be a good chance to get a new licensing philosophy or procedure for non-LWR based SMRs. Now, let me talk about the design and validation capabilities of CARI regarding the sodium-cooled fast reactor development. This slide shows major outcomes obtained from the PGSFR design phase based on the technical capability of CARI SFR team. Regarding the PGSFR development, we have completed the detailed system design and analysis report that is equivalent to SAR safety analysis report. So far, more than 2,000 technical documents have been issued to support its design completeness. For the key technologies dealing with crucial design methodologies for plant safety, dedicated topical reports have been prepared and submitted in the Korean Regulatory Authority, and the review processes have been underway. For the PGSFR design validation, we constructed a lot of infrastructures for safety validation, and total 35 validation programs have been completed as of 2020. And regarding the metal fuel technology, CARI has built our own domestic infrastructures for manufacturing metal fuel components and fuel assembly components. We also have technical expert group, including the R&D area by CARI and industrial support by EXPO ENC and Doosan Heavy Industry. So I'd like to say CARI has enough potential to develop a SMR-based SMR for near-term deployment. As you know, one of the most important things in, one of the most important things in the nuclear reactor development is to verify the nuclear fuel performance. Actually, we fabricated our own metal fuel rod and cladding by ourselves. Then we have been doing neutron degradation tests of CARI fabricated metal fuel rod and cladding in BOR-60 in Russia. So far, irradiation test of metal fluoride up to 7 atomic percent was completed in May 2020, last year, 2 years ago. And we are trying to extend the irradiation test to achieve a 10 atomic percent target burner, including non-destructive examinations. Regarding the cladding materials, irradiation test for FC92 and HT9 cladding was also completed up to 75 dPa in BR16. To make the SFR design more robust, we have identified a lot of technical issues during the PGSFR design phase. As those issues are going much more in depth, needs of experimental design validation and safety demonstration have come up as well. This slide shows the crucial R&D activities by the separate design areas. Among these design validation program, to introduce our 100 test program is a validation test bed for potential cooperation between the international cooperation. Anyway, this final slide shows the lineup of sodium-related test facilities at Carrie. We have various sodium loops or facilities to explore essential sodium characteristics, performance of sodium components, and advanced sodium instrumentation capabilities. As you can see here, Carrie has advanced its own technical capability in conjunction with outstanding infrastructure and R&D-friendly environment. So Carrie is trying to find an opportunity of international cooperation to step forward in technology advancement. Okay, this is the end of my short presentation for introducing the Korean SFR development program. So I would be happy if I can answer your question. Thank you.
Well, I have a short question probably to you. So
Sure.
Our understanding is that your fast reactor focus was on building the burner reactor, right?
Yes.
Because you have the spent nuclear fuel, a lot of spent nuclear fuel to deal with, right?
Yes, exactly.
And I think you mentioned that the decision is still not made regarding the FAST program, right? In Korea,
yes,
it's still ongoing.
Yeah, yes.
Okay, is this a political discussion or technical discussion? What is the underlying problem?
Both of them are the most important in this situation. So, as you may know, Korea is ongoing on nuclear phase-out policy. So there is some, we need some technical and political decision on these issues regarding the spent nuclear fuel management in Korea. So, but the government is not so good on these issues. So we are preparing the next phase of PGSFR development to cope with these kinds of sensitive issues in both in political or technical.
Thank you for this answer, and well, we hope that the technological progress will go ahead, and you will be involved in this technology development in the future. And we have a very good relationship in terms of R&D.
Yes, I agree. That's why we are trying to find some international cooperation partners on these issues.
Thank you very much. And we are moving to the next speaker from Japan, Mr. Yutaka Sakayama, advisor at the Japan Atomic Energy Agency, and he will present on status of Japanese nuclear power and fast reactor development. Mr. Sagayama, are you connected? Yes, we're good. We're good to go. We can see you on the screen. Go ahead. Nice to meet you.
Is it okay?
Yes, we can see.
Okay. Thank you, Chairman. My name is Yutaka Sagayama. Good afternoon, everyone. I'd like to talk about Japanese nuclear power and fast reactor development. This slide shows the nuclear energy in the sixth strategic energy plan, the latest one in Japan. This strategic energy plan was approved by the cabinet on October last year. The outline of this plan is as follows. The first one is the path of the energy policy to realize carbon neutrality by 2050. Necessary amount of nuclear power will be continuously utilized on the major premise of ensuring safety and public trust. And next one is policy responses toward 2030, looking ahead to 2050. The government will follow NRA's judgment. NRA means a safety authority, and will proceed with the restart of the nuclear power plants. Specifically, restart of operation with safety as top priority. And next is the development of fast reactor. Will be steadily promoted by utilizing international cooperation. Other technology are there, small modular reactor technology, component technologies related to hydrogen production by gas-cooled reactor, and R&D of nuclear fusion. This slide shows the strategic energy plan, a strategic roadmap for fast reactor development. Step one is already started from 2019. The main activities promotion of competition. And after this stage, next is a narrowing down and focusing on technologies. And after we will move on the construction phase. Our target is to start operation of a next fast reactor, mid-century. It means around 2050. And after that, latter half of 21st century, we commercialize fast reactor. We are promoting the development of fast reactor by utilizing international cooperation. So for example, multilateral is a GIF framework and bilateral with Russia, France, and the US. Another approach is a NEXIP initiative. We solicit ideas from private companies, private sectors on the fast reactor concept. I will explain later this point. This slide shows the overview of international collaboration. Multilateral collaboration under GIF framework, upper part, and the lower part is a bilateral collaboration. So between Russia and Japan, information exchange for minor actinide transmutation, and between France and Japan, asteroid collaboration, and now we are doing fast reactor R&D collaboration also from 2020. Between US and Japan, versatile test reactor collaboration. Memorandum of cooperation was signed between METI, MEXT, and DOE in June 2019. But unfortunately, versatile test reactor is not so go smoothly. And Japan is also discussing cooperation with TerraPower's natrium reactor. Next slide shows the NEXIP initiative. This is a Japanese initiative to accelerate nuclear innovation. This is a new initiative to help accelerate the development of innovative nuclear technologies through funding support, access to R&D facilities, and human resource development efforts. NEXIP initiative is implemented with the support of METI, MEXT, and JAEA. The contents are as follows: funding support to R&D, new reactor design concept, accompanying technologies, for example, safety and so on. Access to R&D facilities, JAEA research facilities, reactors, and databases. Collaboration with universities and international community. So last one is a human resource development. Now we are pursuing competition among various technologies through NEXIP initiative. And there are so many ideas. Modular LWR with passive safety, and fast reactor, it means a sodium-cooled fast reactor mainly, and effective use of resources, and also high-level radioactive waste management. And also a high-temperature gas-cooled reactor for hydrogen production. JAEA offers facilities for the development of these concepts. We introduce JAEA's fast reactor cycle R&D facilities and efforts on R&D. Upper part, left-hand side, Planter and Athena. These are sodium test facilities for the demonstration of large sodium component and natural circulation phenomena and so on. And right-hand side, fuel fabrication to develop remote mine actinide bearing MOX fuel fabrication technology. So we have a plutonium fuel fabrication facility and the plutonium fuel development facility, and also hot cell AGF. With regard to reprocessing, we are pursuing development of minor actinide partitioning process and performance evaluation. We have chemical processing facility. And lower side, left side is a fuel and core material development and irradiation test by using JOYO, and also fuel monitoring facility for post-irradiation examination. Unfortunately, JOYO now stopping, but JOYO is under review by NRA for the restart. The target of restart is 2024 at the earliest. Sometimes slightly delay, in this case, 2025, for example. And next slide shows the potential role of JOYO as a versatile research platform. JOYO work for the support NEXIP initiative for the technical innovation and production of medical and industrial isotopes and human resources development, and R&D for fusion reactor, and the minor actinide transmutation for sustainable use of nuclear energy, and for utilization of separated plutonium for a world free from the threat of nuclear proliferation and terrorism. Last slide shows the Athena facility of sodium test, the large-scale sodium test facility for the component development and demonstration. Dimension is 130 meter multiple 60 meter and 55 meter height. Sodium inventory is 240 tons. And sodium heater is 60 megawatt at maximum. We already available mother roof. And now we are constructing sodium heater. Around 90% is completed. We will finish within this year of this sodium heater or beginning of next year. Thank you very much for your attention.
Thank you, Mr. Sagayama, for your presentation. Yeah. We see the direction where you're moving and we see the VTR project on your roadmap. But you know that you're always welcomed at the REC Beer Consortium. Just a quick comment from me there. But and we understanding that you're studying the JOYO as well on the way to do it. So all these activities that Japan is doing right now in relation to the fast reactors, does it, and I hope I'm not asking an easy question where you're going to say yes, but do you feel this need for the fast reactors? And can you say that Japan is on track to move towards developing this technology and launching commercial operations? So this is set as a national goal. Could you confirm that it's a made decision?
Yeah. Basically, so fast reactor and its related fuel cycle is our real target for the future. So nowadays, we use light water reactor and reprocessing facility also. Unfortunately, not started, but we hope this by the end of this year. And after that, we have to construct fast reactor and fuel cycle also. And of course, now we are doing another ideas. Idea means another concept of gas cooled reactor for the hydrogen production. And this is another candidate for the future. But main part is a fast reactor and fuel cycle.
Well, thank you very much for this answer, and thank you very much for your presentation. We're a little bit running behind the schedule, but we're moving to the next presentation from Mr. Akas Horvat, Allegra Possibilities for European Energy System of the Future. And Mr. Horvat is the Director General Center for Energy Research of Hungary, the V4G4 Center of Excellence. So if we can have Mr. Akas on the screen.
Mr. Chairman, thank you very much. I'm sharing the presentation.
Yeah, thank you so much. We can see you and hear you well, and we can see your presentation. Go ahead.
So, Mr. Chairman, it was several times mentioned during this session that the main goal of the nuclear technology future is maybe the closure of the fuel cycle. So answering the questions how we provide the fuel on the long term, and also how we manage the spent fuel. And my presentation is another answer, so it is not much differing from the previous ones, except that I will speak about a gas-cooled fast reactor system. In the name of the V4G4 Center of Excellence, this is a consortium of partners from Central Europe, plus France as an associated member. And the demonstrator reactor is called Allegro. And I'm going to the next slide. So the main question why we speak about this gas-cooled fast reactor instead of the other technologies. Of course, we know very well that sodium and the lead technology has much more experience. But we think that the gas has some advantages in some cases concerning, for example, that it is chemically inert. The void coefficient is small, so from safety point of view, gas has some advantages. On the other side, the gas coolant like helium or CO2, for example, has a little thermal inertia, so the rapid heat up and the loss of cooling is an issue. It gives some challenges for us for the design. And also because of the high temperature, high outlet temperature, the fuel development is also a challenge. You can see here that what are the main goals, the main objectives of the Allegro project, which aims at building up the demonstrator fast reactor of gas cooling. First of all, demonstration of the concept at all, that the fast reactor cooled with gas instead of molten metals is viable. The other objective is the proof of the technological feasibility. Also, it could provide a testbed for new materials and technologies. And also it is important for at least one of the partners that the test of process heat utilization, hydrogen production, for example, but we can speak about other uses as well. So we think that the first step should be the Allegro as a demonstrator, a small reactor, a small device, before we go for a bigger one, the commercial gas-cooled fast reactor, the GFR system. You can see the partners here from Central Europe. We have the Polish, the Czech, Slovakian, Hungarian nuclear institutes. And also we have the CEA and the French smaller institute as associated members. So together we form the V4G4 Center for Excellence, because V4 is also associated with the so-called Visegrad group. So it is a common name for these 4 countries in the Central Europe region. Some numbers, some figures about the Allegro. The parameters are very similar to other demonstrators. So the power is a few 10 megawatt, and we calculate about with 850 degrees outlet temperature, which is quite high. It is aimed that this high temperature can be used for hydrogen production or other process heat. And we are calculating with a relatively large power density in the core. So this gives, of course, some challenges. First of all, we have to start somehow the demonstrator. We think that we can start with MOX fuel in the first step, and then build up another core with refractory fuel in the longer term. So a few words about the specific challenges, like the thermal inertia, low thermal inertia of the coolant, and also the very high power density. So in this gas cooled system, we need to implement a better decay heat removal system. This is one of the objectives of the design work now, and also we have to think about refractory fuel with ceramic or other heat-resistant cladding, and of course all the details which is listed here, but I don't have too much time to go into details this time. You can see some drawings of the specific safety elements, like the guard vessel, which encapsulates the whole machine, the whole device, the liquid reactor, in case of a low pressure scenario, low pressure accidental scenario. Also, the decay heat removal system has a drawing in the middle, which is a specific feature of the gas-cooled reactor, and also the emergency coolant injectors connected to the main loops. Some figures about the guard vessel here. It is quite a large volume, which is designed for encapsulating the whole machine, and it provides the safety features, a safe framework for in case of an accident. Of course, it is a question how to manipulate inside the guard vessel at the same time. So this is a question for the designers. The safety of the gas-cooled reactor seems let's say, possible. Safety features seem to be viable, but of course, we have to add some unique features, a core catcher, DHR loop, for example, a battery power blower, in case when we lose the electricity of the plant. The Rosatom in Europe is also supporting this project and the effort. For example, presently we are running a SafeG project in Europe with the partners. You can see the logos of them at the bottom of the screen. This SafeG is aimed at developing the scientific background behind the design of the Allegro, also forming a much more stable competence behind this concept. We have 15 organizations from 7 European countries, plus Japan is on the board. And this project started in 2020 and lasts until 2024. The main objectives you can see here in the work packages, the core design and safety assessment, innovative materials, decay heat removal, and of course we have to speak about the standardization and codes on the long term, as we all know very well that the present codes, safety codes, won't be valid on the long term if we speak about these innovative designs. So we have to mention that the reactor codes also should be developed for all the technologies. So it was the Allegro project in a nutshell, very briefly. If you have any questions, I'm waiting. Thank you very much.
Yeah, thank you very much, Mr. Horvat, for your presentation. I have one question. When you're going to be, if of course, moving towards the application and building the reactor itself, do you feel that you need the infrastructure such as independent loop with gas coolant in some research reactor to conduct the research needed for the regulators to give a green light for the construction of the reactor?
Yes, basically we all know that the fuel qualification will need such a specific loop and a research reactor somewhere else. So we are looking forward to find the best place. Also, MBU is among the we consider it. Let's say several years long qualification program will be needed before the run or the commissioning of Allegro, and then Allegro can also serve as a testbed for the future development. But first of all, I'm sure that we will need some other facility.
Well, thank you very much for your answer, and good luck to the Allegro project. We are all looking at it with lots of interest. And our next speaker is Mr. David Nichols from NEXA, South Africa. He is the board chairman and will be presenting of the high temperature gas reactors in South Africa.
Thank you very much indeed. I think I'm presenting one of the, what's the right word for it? More historical discussions. But if I may share my screen, just quickly, I apologize for being slow. Right, is that screen visible?
Yes, we can see and hear you well.
Okay, right, thank you. Yeah, I'm not only the chairman of NEXA, but for about 15 years, I was the director of the PBMR project in South Africa. So my background in working for the power utility. So that's my background. Just quickly, I want to start with the end of the project, which is looking at the PBMR design that we put forward. And I won't go any further than this because time is clearly limited. So I want to go briefly through what the South African nuclear background at the moment is, where we stand, the history of our HDGR work. The test rigs we established, which I think is one of the key issues, is validation, verification of the analysis that's been done. Some of the key technical issues that I think have been hopefully helped in the international community by the work done in South Africa, and then possibly the way forward in South Africa. I recognize time is an issue. So basically in South Africa, there are two major nuclear bodies, as well as the regulator and the Waste Disposal Institute and research institutes. There is NECSA, which stands for South African Nuclear Energy Corporation, established in 1948. Safari, we've got a reactor called Safari 1, which is a 20 megawatt pool reactor commissioned in 1965 and still operating at the moment, achieving at the moment something over 300 days on load every year. There was established a domestic uranium enrichment program in the 1970s, which was closed down in the mid-80s. There was also a domestic fuel fabrication facility established in the 1980s to provide fuel for our Coburg nuclear power station. That again was closed down for economic reasons in the early 1990s. At the moment, NECSA's probably biggest claim to fame is that it supplies some 20% of the world's radiopharmaceutical supplies, and is one of the key commercial activities of NECSA. The other issue in South Africa, which is of note, is the Coburg nuclear power station. It's a 2 by 920 megawatt PWR Framatome construction to a Westinghouse design, standard 3-loop, ordered in 76. Unit 1 commissioned in 84, Unit 2 commissioned in 85, and we plan to operate in 2024. In fact, Unit 2 just shut down after 452 days on load, and is changing steam generators, which is also interesting because we are the last utility to change our Inconel 600 millennial SGs, which are still in good shape, but we're changing those and upgrading the plant. So what's our high temperature gas cooled reactor work? In about 92, there were initial studies by a local company into a sub 5 megawatt pebble bed high temperature gas cooled reactor. In 95, ESCOM, the state power company, which I worked for 35 years, initiated studies onto a 100 megawatt high temperature gas cooled reactor. And I must comment one of the funny statements when we first went to Vienna to the IAEA and we discussed a 100 megawatt commercial nuclear plant, we were told that was impossible because they'd decided that all reactors fell into one of 3 categories. Large was above 1200 megawatts, medium was 900 to 1200, and small was 600 to 900, and there was nothing below 600. The world has changed since then. In 1999, British Nuclear Fuels and Exelon, the big utility, and also ITC, which is an investment corporation in South Africa, joined the ESCOM project, which was approved by the South African cabinet in 2000. By 2002, we had a 400 megawatt thermal, 165 megawatt electrical design established. I won't be going into vast details. It was a direct cycle machine, and was supported by a very large number of large industrial corporations, Mitsubishi Heavy Industry on the turbines, for example. And by 2006, component manufacture for the first unit was initiated. In fact, unfortunately, due to various reasons that were not related to the technical side of the project was put into care and maintenance in 2010, where it's in fact still is. In 2016, ESCOM initiated studies into what might be an advanced high temperature reactor, and I won't be discussing that much. It's actually in the IEA document mentioned earlier. But what's really interesting is that in 2019, South Africa's integrated resource plan, which was approved by cabinet, calls for 2,500 megawatts of nuclear power in a modular approach. Just to put the South African effort in scale, by the time the project was closed, the staff numbers in the project peaked at about 900, and the total spend on the project was around $1 billion. So I think what I want to discuss a little bit of time, and I'm aware we're running a bit late, is some of the facilities that were put together by this project. Probably the most important one was the TRISO fuel production facility, 5 kilogram coater. I think it's still the biggest actual physical coater in the world. Was established and commissioned along with all the other facilities to do a research laboratory. A helium test facility. This is still in existence, and these the TRISO production facility is still in place. It's in care and maintenance, but it's still in good order. The helium test facility, 95 bar, peak temperature achievable 1100 degrees centigrade, and 43 meters tall, so you could install complete components for a large HTR in the project. It is notable that facility again is in care and maintenance. What is interesting is that in terms of engineering quality, the helium charge that was put into the plant in 2010 is still in place. The plant is still pressurized and has not actually been topped up since 2010, which for a helium cycle is quite interesting. The project also built a pebble bed micro model. It was a 3-shaft closed cycle Brayton gas turbine. Again, there was a critical test assembly created at the Astra facility in Kirchdorf. That was in 1998, 1999, I think. For the first annular core, we know that we're in critical. A series of heat transfer facilities, full-size fuel handling systems, and many equipment facilities. Just some reasonably large, quick photographs. Photographs of some of the coater facilities, fuel sphere labs. This is just some work we carried on after the project went into the thing. This actually is a coated particle which has been milled by focused iron beams, and you can see the level of detail we're down to there. Helium test facility, there's a picture of it. It's on the Nexa site. Said 43 meters tall, 95 bar. The main loop runs at 660, but we get 11 degrees centigrade in test sections and 9.5 kilograms a second at 95 bar. Micro model, this was built to test to validate the computer codes on the functioning of the 3-shaft gas turbine. This is rather bad. I apologize for the bad photograph of the top of the Astra facility in Kirchdorf. The core loading device, fuel handling, and so on. A lot of work was done into the simple thing that is often forgotten about, is that under a high pressure, high temperature helium environment, you actually get self-welding of components. So proving the functioning of valves components under the full helium situation was quite an important issue for us. So what are the key technical issues that I think can be were addressed or put forward by the PMR program? First one was TRISO fuel performance. We built fuel. It was sent to Idaho National Labs for irradiation, and then PIE at Oak Ridge. Extremely good results. I won't get details on that, but I think what is vitally important is that the concern of the HDR programs that high temperature gas core reactors, TRISO fuel, if you go back to, let's say, 1990, there was concern that it was very much, it depends on how it was made. It was very careful as to how you actually could make this reliably. And I think that the application of modern QA technology and standardization has allowed us to move fuel forward. So we now are pretty confident in TRISO fuel performance across the world. And it's very nice to see the US DOE commenting strongly that it is the ultimate fuel in terms of integrity. That comes to the second one, which is TRISO fuel production repeatability. Again, if you go back to the 1990s, there was a view you had to physically qualify every piece of production equipment with more irradiation testing because of the uncertainty in production. That I think has been got rid of. Heat transfer in pebble beds. A lot of work was done to prove the heat transfer because the safety case of a pebble bed reactor is based upon if you fully depressurize and do you have enough heat transfer out of the pebble bed to keep the fuel below its failure point. And that's shown to be the case. It is worth noting that in a pebble bed reactor, the classical limiting accident is all the rods are withdrawn fully at full power, followed by complete rupture of the main pipework, followed by no intervention of any kind thereafter. As I mentioned, equipment performance in high purity helium is a major issue. You get, you lose your oxide layers, and therefore you can get literally welding of valves after a single cycle. Two other things that I think can't be underestimated. A lot of work was done in Germany in the 1960s, 70s, and 80s, which was, a lot of it was empirical information, and it had to be revalidated because it was fully an appropriate technology approach taken in the 60s and 70s. But in reality, by the time you got to the 2000s, you had to get better validation of that data, and that's been largely done. And we did a lot of work with ASME specifically in terms of design codes to get approval for design codes for graphite and such things, which didn't exist in modern science.
Mr. Nichols.
Last slide.
Okay.
Yes. Last slide.
Yeah. Okay.
Sorry.
Sure.
Go on.
Yeah. Go ahead. We're a bit tight on time, but let's sum up.
Very quickly. Way forward for it is South Africa's got a resource plan which calls for 2,500 megawatts of nuclear power. A request for information was issued in 2020 by the government for PWRs and small modular reactors. The DMRE has expressed an interest, an intention to issue a request for proposal in March of this year, and they should include an SMR option. The minister has called for the commercial closure, that is the contracts to be in place by 2024, and consideration to be given to replace the current intended inland ESCOM coal fleet from 34,000 megawatts of coal by potentially SMRs by about 2040s. It is notable the SMRs are not committed to being an HDGR type design, but that clearly would have some advantage in South Africa because of our technological base. And I will thank you, sir.
Well, thank you so much for your presentation. It's very interesting to see your goals in terms of future development. Very quick question, maybe yes or no. We see that you have lots of background knowledge on the gas-cooled reactors. Are you planning to, or South African scientists planning to participate in some joint activities in this area, joint research?
I think at the moment, not specifically. We're very much more looking in the straight commercial activity of trying to get SMRs on the ground and working and making power. There are I will comment that in other HDR high temperature programs like Kairos and X-Energy, you'll be surprised to find how many of the ex-South African engineers are actually present in those. And in fact, one of the US projects, USNC, has its engineering offices in Pretoria. So we're still functioning at an industrial level. But no, I think the research side is still very much seen as, we'll have to see what comes out of any proposals this year on the commercial basis, and that might well induce some, but at the moment there's no short-term aim for that.
Thank you. Thank you for this comment, and thank you for your presentation. It's very interesting. And we're moving to the last presentation of the day from Mr. Valery Shevtsov, Director of Frank Laboratory of Neutron Physics in Joint Institute of Nuclear Research. Mr. Shevtsov, the floor is yours. Let's try to keep it in 10 minutes strict, and we're going to go into 3 minutes summary at the end. Thank you. Valery, we can see you, but now.
Sorry, Mr. Chairman, I had some problems with my Zoom software.
No, it's okay. We can see you.
Now
we can see you well, and hear.
Okay, now I will try to share my presentation. Okay, now it's done.
Yes, we can see the presentation. Go ahead.
Good afternoon, everybody. Good morning. I would like to give you some information. How can we utilize the neutrons which are produced at our reactor facilities? It happens that with the neutrons extracted from the reactor through the experimental channels, we can do a lot of interesting things, and we have a lot of we have many international centers with neutron sources of different types, including research reactors and spallation sources and other. And I will briefly inform you what can we do with this extracted neutron. First, I would like to introduce my organization. I'm working at the Joint Institute for Nuclear Research. It's an international intergovernmental organization, which is located at Dubna city in Russia. And this organization unites 25 member countries. 19 member countries full-fledged, and 5 member countries so-called associated members. And just last November, about 2 months ago, we were lucky to get new member country among our full-fledged members, and this is Arab Republic of Egypt. They become the full member country. In this organization, we have about 5,000 staff employees, 7 big laboratories. One of the laboratories is a laboratory of neutron physics, which I am representing here. And this laboratory possesses the fast pulsed reactor IBR2. On my slides, in the left down corner, you may see the animation of the fast reactor, and later I will explain briefly how it works and what are the advantages of this machine. So when we are talking about the extracted neutron beams, we have to keep in mind that the neutron wavelengths, the wavelengths of neutrons which we are using in our research, expands from Fermi 10 to minus 13 centimeters to micrometers, thousands of angstroms. And in the laboratories, we can use all these neutrons in order to investigate the internal structure of the objects, scaling from atomic nuclei and crystals and molecules and nanoparticles and some constructional materials and some real constructions. Our IBR2 reactor operates in periodically cycling mode. It flashes 5 times per second, and having the average power of 2 megawatts. The peak power, which corresponds to the maximum of the neutron flux density during the peak. The peak power is almost 2 gigawatts. You see, it's 1850 megawatts. You can imagine it's almost 2 blocks of power station compressed into the very small volume, because the volume of our reactor core is only 22 liters. That's why the neutron flux density on the surface of moderator of our reactor is almost 10 to 16 newtons per centimeter square per second, which is an order higher compared to the most intense steady-state research reactor operating at ILL institution at Grenoble, France. Around the reactor, we have 20 instruments. We have 14 beam ports, and we have 20 instruments located around the reactor. Most of these instruments are dedicated for the research in the condensed matter physics. By means of neutron scattering, we are investigating the structure and dynamics of the different objects from condensed matter physics. Most of these instruments are proposed for international scientific community through the user policy, which we have in our laboratory. 2 times a year, we're announcing the call for proposal. We are accumulating the proposals through the web interface, and later these proposals are evaluated by the international independent expert community. And in case if proposal has good marks from the experts, we are providing the beam time without charging the scientists. We are not taking money for the beam time, and moreover, for the scientists from the member countries of the Joint Institute for Nuclear Research, we are providing local support during the experiment. In total, we have about 500 experiments on all these instruments, and more than 200 of these experiments are done by external users, which are coming through this user program. The main directions of the research I mentioned is mostly condensed matter physics, the physics of nanoscale phenomena, physics and chemistry and functional materials, biological research, including complex liquids and polymers, and biological membranes, soft condensed matter, and more engineering directions, functional materials. Very important task which we can perform with our diffractometers is a non-destructive control of residual stresses and strains in bulk materials. One of the examples of the research which we have at our reactor, some kind of applied research, diffraction studies of lithium batteries. It happens that by means of neutron diffraction, we can look in real time how the process of charging and discharging of the lithium battery happens, and we can look by means of neutron diffraction how the composition of the electrodes and electrolytes is changing during the cycles of charge and discharge. Here we can see the interplanar distance in angstroms, experimental time in hours, and several cycles of charging and discharging the battery. And the different color at this diffraction pattern tell us about the diffraction peaks. And these bright spots are diffraction peaks from this phase lithium carbon 6 on anode, which appears only if we are doping one of the electrodes with a very small amount of vanadium. You see the vanadium concentration is less than 0.1%. But namely this doping by vanadium gives the new properties to this lithium battery. It increases the number of charging discharging cycles and increases the capacity of this battery. So this is one of the examples how we can utilize the extracted neutron beam. More traditional way is coming from a nuclear physics. By means of neutron time of flight method, using the pulse sources, we can measure the cross sections of different isotopes and different constructional materials. And these data, nuclear data, are necessary for substantiation and calculation of the properties of future reactors and future nuclear installations. So coming to the conclusion, I can tell that using the extracted neutron beams, all this variety of the research which you see on this slide, you can do very effectively. And in our laboratory, we are doing that. In our institute, we are doing that. And last year, we are in a good contact with the MBIR consortium. And we are looking for the joint research program for utilization of the extracted beams at the MBIR reactor. And we are looking for synergy in such a research at MBIR reactor and future GNR pulse reactor IBR3, which has at the moment name Neptune, because we are planning to build this pulse reactor based on neptunium nitride fuel. So here I'm finishing my presentation. Thank you for your attention, and I'm ready to answer the questions if you have.
Well, thank you very much, Mr. Shvetsov, and thank you very much to all the speakers today. Unfortunately, we don't have time for any follow-up questions, but we are very happy that we're working together between IRC, MBR, and Joint Institute for Nuclear Physics Research. And I wanted to sum up in the next minute what we can take from this panel discussion is that new nuclear technologies are under development, and we can expect the turning point in the 21st century when we're going to see more new technologies on the market and more commercialization of the fast reactors as well. And all of this will push the demand for the research infrastructure by the mid of 21st century and in the 21st century. So it is very important to be ready for this spike in R&D and commercialization, and we think that the infrastructure that we're putting together as Russia and Rosatom will answer these questions and goals and demands of the market. So once again, thank you very much to all the speakers. If there will be any follow-up questions from the people who are going to see this on YouTube and other platforms, we're going to send it to you. And we wish you all the best with all the projects, and we hope that together we will bring the nuclear energy to the next level. Thank you so much for the audience who've been here, and I hope that the next panel we're going to have face-to-face and not in this mix online, offline. So thank you very much, everybody.
Thank you.
Thank you.
Thank you.
It could have been if you'd only